Hello, am I audible to you? Yes, Mayur, please reply me. Am I audible?
Yes, sir.
Okay. I think you have seen the video and whatever the readings I mentioned in the video, you have noted it down. And we will see the calculation part of that experiment, that is determination of the thermal conductivity of metallic rod. We have used copper as the material for that rod, and the entire experimental setup that I have already explained, in what way we have to take down the reading, where we have to take down the reading, temperature T1 to T9, and then T10 and 11 are the temperatures of cooling water, then voltage, current, the flow rate of the water, and the flow rate in the sense by measuring the volume that is flowing in a given period of time. So if you have noted down all these readings, then we should proceed to the calculation part of that experiment. But before I proceed to the calculation part, let me know if you have any doubt, any question related to the experiment, then please let me know. I will explain it to you. Yes, any doubt? Okay, fine. So let us begin, considering that you don't have any doubt related to the practical or the experiment. So I'm proceeding to the explanation of the calculation part of that experiment. What calculation? Okay, what happened to this? Hello, am I audible now?
Yes.
Okay, fine. So let us proceed to the calculation part of that. Now this is what the name of the experiment, and well, so determination of the thermal conductivity of metal rod. In previous experiment, we have seen the determination of thermal conductivity of insulating powder. Here we are going to find out the thermal conductivity of a metal rod. So we have used copper rod, copper as the material for the for to find out the thermal conductivity. This is what the theoretical part I have already explained. We have seen in detail. Now the thermal conductivities of some of the typical materials is given over here. So out of that, the copper rod, pure copper, has a thermal conductivity in the range of like 390 watt per meter per Kelvin, and that too at this temperature. Now why this temperature has been mentioned over here? The thermal conductivity is also the function of temperature. So at one particular temperature, say 20 degrees Celsius, the thermal conductivity of copper rod is this much, right? Now, this is what the theoretical value that we have, that we know already, that is given in the book, or say anywhere you can get it. Even if you Google it, you will get this number. Whereas practically, how much is the thermal conductivity of copper, that we are going to find in this experiment. Now, the diagram, you have seen the experimental setup. Now here you can see, this is the cross section of the metal rod. Now in the video you have seen that there was a setup, and one end of the rod was fitted inside the heater and other end was towards the cooling jacket. So over here you can see there is a heater. A heating coil is wound over this end of the rod, and we have given somewhat voltage supply to it so that some current starts to flow through it. As somewhat current flows through this wire, it will give some heating effect, and due to this heating effect, the heat is get produced also that given to that this end of the copper rod. The total length of the copper rod is 350 mm. You can see from this end to this end, the total length of this copper rod is 350 mm. Out of that, the length of the copper rod which is under our observation is only 200 mm. You can see this is 200 mm over here. Now this 200 mm length of the copper rod is provided with the insulating powder. This insulating powder has been given filled in the surrounding region of that copper rod, so that there should not be any loss of heat to the surrounding, that is in the radial direction. So the Q in the radial direction over here, heat transfer rate in the radial direction is 0. Next, as the total length is about 250 mm, so the total length is 250 mm. Surrounding to it, there is insulating powder over here, and we have fitted about 9 thermocouples separated by a distance of 2 centimeter. 2 centimeter, and from this end, I mean, you can see this from 2 centimeter over here. This is the first thermocouple, second thermocouple, third, fourth, fifth, and up to ninth. So every thermocouple will measure its temperature at that particular location at that particular instant. Now, no need to say instant, since this experiment we are conducting under steady state condition only. So obviously the heat will start to flow, so as there is a insulating material in the surrounding region. So heat will flow in this direction. In this direction, the heat will keep on flowing, that is Q dot, and finally it will come at this end. Now you can see there is a cooling jacket over here, to which we are providing the cooling water which is at the temperature T10, and once the cooling water is given to this end, that cooling water will absorb the heat from this end and will take away that heat to the next pipe. And here again there is one more thermocouple which can measure the temperature of the cooling water outlet, or the cooling water out. So we have the temperature, we have the temperature T10 over here. This is T10 and this is T11, which measures the temperature of cooling water in and cooling water out. And while the water is flowing through this region, it will absorb the heat from this rod and will take away that heat, right? So all these temperatures T1 to T9 and T10, T11 we can measure. So this is all about the figure. Next one, the experimental setup that I already explained, what safety precautions we have to follow and what procedure we are going to follow, that we have seen. Now here there are some given parameters. The parameters are the observation, the material of copper rod, the material for the metal rod is copper. The length of metal rod is 350 mm. The test length of the bar is 200 mm. Next, the diameter of the metal rod is 25 mm. It means that 25 mm means it is 25 into, this is 25 into 10 to the power minus 3 meter. By the way, if this much is the diameter, can anyone tell me how much is the cross-sectional area of that rod? See, this is the metal rod. This metal rod has the diameter. Someone please take down the calculator and find out how much is the diameter of this pipe. I mean, not pipe. The diameter of the copper rod. So this diameter 5 over here, is equal to 25 mm. So how much is the cross section of this rod? Can anyone tell me how much is the cross sectional area? The cross sectional area will be equal to pi by 4 d square. So this is equal to pi by 4 into how much is the diameter? Diameter in terms of meter. So it will be 25 into 10 to the power minus 3 whole square. So the area of cross section of the copper rod is, can anyone tell me about that?
4.90 into 10 raised to minus 4.
Okay, just a minute. Simultaneously, I am also calculating it. So this is 4.90 The area is, it is 4.90 into 10 to the power minus 4 meters square is the area. The area of cross section. This we are going to use in the final calculation. Next, what voltage and current reading you are getting? Okay, there is one more set of reading nearby me. That reading I would like to tell you. Shall I tell you? Hello?
Okay.
The supply voltage that I had kept in one more, see, just for to give you the accurate reading, I was needed to perform this experiment multiple times just for to bring the steady state condition and to have the accurate reading. And in the most accurate reading that I got in last 2 days is over here, and I'm going to tell you these readings. So the input voltage is 100 volt. The current for that much voltage was 0.382 ampere, and the flow rate of the cooling water was just a minute. The flow rate for the cooling water, it's not, I mean, it's not the flow rate directly. The volume which was flowing, I got it to be, it is 250 ml, and the time needed for that much flow of water was about 100 seconds. So from this we can calculate the flow rate. This flow rate over here is equal to the volume which is flowing. This is 250 ml. Let us convert that into meter cube. So it is 250 multiplied by 10 to the power. How much it will be? Yes. ml का लीटर में करना है, यूनिट मल्टीप्लाइड बाय 10 to the minus 3, और लीटर का मीटर क्यूब में करना है अगेन मल्टीप्लाइड बाय 10 to the power minus 3. So इसका मतलब है 10 to the power minus 6 divided by this is 100. So what result you are getting? The flow rate you are getting it to be equals to how much you will get? I think this will be 2.5 into 10 to the power minus 6 meter cube per second. Right? So this is the flow rate of water. Next one. Now the temperature readings, I would like to give you only the last temperature reading, since earlier temperature reading from first minute, 10, 20, 30 minutes, they are not important. Only final readings are important. So I will tell you only the final readings. And that too, I got that final readings at, I mean, almost steady state condition at 135 minute. 135 मिनट पर, मतलब लगभग 2 घंटे से भी ज्यादा रखने के बाद मुझे रीडिंग्स आ गई है. So these readings are T1 is 65.3. Obviously all these are in degrees Celsius, so I'm not going to mention the unit over here in this row. T2 is 63.7. T3 is 61.4. T4 is 61.3, 61.2. T5 is 59.5. T6 is 57.9. T7 54.7. T8 53.5. And this T9 is 52.1. So these are the readings of along T1 to T9 thermocouples. Ti, temperature of water inlet, is 30.3. It is 30.3, whereas it is 30.5. I mean, sorry, 32.5. T, sorry, it's not 12. It's T11. So this is 32.5. 5 degrees Celsius. So all these are the temperature readings. Now let's have the calculation part. How much is the mass flow rate of the water? Mass flow rate of the water can be obtained by simply multiplying. Okay, this we have not followed. This we have not followed. Mass flow rate of water. Now you have the volume flow rate of water. You have the volume flow rate of water. How much is this? It is 2.5 into 10 to the power minus 6 meter cube. So meter cube per second. So to get the mass flow rate, you need to simply multiply it by. But to get the mass flow rate, I will write it over here. The mass flow rate MW is equals to the volume flow rate. See, this don't get confused with this volume flow rate V, क्योंकि यहाँ पे volume flow rate को लिखने के लिए Q भी नहीं लिख सकते क्योंकि यहाँ पे Q represent करता है heat transfer rate को और ये जो V, let us say it is V1, better way, so that you will not get confused with the voltage V and the volume flow rate V. Let us say volume flow rate ये जो है ना, let us say this is V1. And this one is regular V. See, there are two V's, both V's are capital. So, ये जो capital V है, that is the voltage, and this V1 is what? The volume that is flowing, the volume of the water that has flown in 100 seconds. So that V1, sorry, this is V1, V1 dot दे देते इसे, the flow rate, V1 dot. So I can get the mass flow rate MW dot is equals to the volume flow rate into the density rho. So this is equal to, how much is the volume flow rate? Volume flow rate we have already calculated. 2.5 into 10 to the power minus 6. So it is 2.5 into 10 to the power minus 6 multiplied by density of water is 10 to the power 3, considering, I mean, the standard density of water. And you will get the mass flow rate to be, this will be, it will be 2.5 into 10 to the power minus 3 kg per second. That much is what the volume flow rate, sorry, mass flow rate. Once we get the mass flow rate, we can get the heat transfer rate. How it is? The heat transfer rate will be equal to MW. MW we have just obtained, that is 2.5 into 10 to the power minus 3. This is the mass flow rate into CPW, that is specific heat of water, is 4.187 kilojoule per kg per Kelvin. But if I convert that into SI, it is 4187 joule per kg per Kelvin multiplied by temperature T11 minus T10. T11 is 32.5, sorry, 32.5 and 30.3. So this is 32.5 minus 30.3. So this is the calculation. So can anyone tell me this number? Yes, anyone? I am getting this value to be, someone please verify it, 23.02. 23.023 watts. Yes. So that's what the heat flow rate. Am I audible to you? Hello? Am I audible? Someone please reply me.
Yes, sir.
Yes, Sagar. I can't hear you.
So you're audible, sir.
No, I can't hear you. Please let me know. Am I audible or not? Someone else reply me. Mayur, Pranay.
Audible, yes, sir.
Okay, fine. So keep on replying. Well, so हम बात कर रहे थे कि heat gained by the cooling water means what? That much is what the heat transfer rate. So out of that now, if you take down the Fourier's law, that is Q is equal to minus Ka dt by dx. Okay, one more part we need to calculate, that is dt by dx. Now dt for that rod, if you check out that rod, metal rod over here, dt by dx is nothing but, see, this is here, let us write down this dt by dx. हमें exactly इसका word to word meaning तो नहीं ले सकते अभी यहाँ पे क्योंकि वो derivative है. So let us say instead of this, let us take down, this is delta T for rod divided by delta X. Delta T by delta x for the rod. तो ये क्या आ रहा है? Delta T will be equals to the temperature difference. How much is the temperature difference? It will be T1 minus T9. It will be T1 minus T9 and divided by delta x will be, how much will be the length, this length? I think, how much will be this length? Can anyone tell me? This will be 16 centimeter, means it is 0.16. Are you getting this? This is 0.16 meter, right? So how much? Oh, I mean, this is 0.16. So how much you will get this? This is T1. You know how much is T1? I think we have right 65.3. This is 65.3 minus T9. T9
52.1.
52.1. That's good. It is 52.1 whole divided by, this is 0.16. So how much is this?
82.5.
This is equal to 82.5. Is that okay? Are you sure? Is this the answer?
Yes, sir.
Okay. 82.5. So dt by dx, I'm going to write down here dt by dx. Here we are going to write down dt by dx. Dt by dx is equal to, how much is said?
82.5.
It is 82.5. Next, area of cross section that we got over here. How much was the area? We have calculated it. It was 4.9, right?
4.908 into 10 raised to power minus 4.
Into 10 to the power minus 4. I mean, meter square. This will be in terms of degrees Celsius per meter or say Kelvin per meter. Next one, what else is needed? Area pata hai, dt by dx hai, q pata hai. So only you need to find out is, only unknown into this equation is k. So I would like to put on the values of this k, sorry, q is equal to, this is 23.03 as equals to, this is k, the thermal conductivity, into the area is 4.9 into 10 to the power minus 4 into dt by dx is, I think it is 82.5. So the only unknown in this equation is k. So can anyone tell me, can anyone calculate and tell me the value of k?
$569.69.
569.69. Are you sure? Yes.
569.69.
Okay, if this is the case, then we must have missed some part, some calculation part. Somewhere we must have gone wrong, or maybe there is somewhat error into the measurement. Something is going wrong. Since the thermal conductivity of the copper material, we know that value. It's about 390 watt per meter per Kelvin. So it has to be close to 390, not more than that. ये possible ही नहीं है. 500 के रेंज में अगर आ रहा है तो more than 500, right? Hello, hello, I'm audible. I'm audible to you.
Yes, sir.
Everyone, please check out the calculation. Q we are getting it close 22.6 यहाँ पे 23.03 आ रहा है. dx okay. Okay, fine. So whatever the results are, they are. So even the reading, in a case if this reading is wrong, then we need to go. I mean, obviously it is not the correct one. So we need to go for the experimentation once again. We will perform the experiment. We will take down the reading once again, and we'll have the calculation until and unless we will get the answer close to the actual value of the thermal conductivity of copper, which is 390. So whatever the value that I got last time was of 263. 263 is not, also not close, but it's okay. We can just justify it by saying there can be some error in the measurement. But 500 is far away from it. Right? Hello? Am I audible?
Yes, sir.
Okay, one more thing that is yet to be completed. Plot the graph for the temperature in degrees Celsius from T1 to T9 on y-axis and length in mm along x-axis. So what you need to do is you need to show the variation of temperature with respect to the distance or with respect to the length of the rod. Let's say this is the y-axis. This is the y-axis, and this is the x-axis. This is the y-axis. Here the temperature in degrees Celsius. It is given along y-axis, and here it is the length of the rod in mm or centimeter, whatever the unit you want to follow, you can. So these lengths and these steps will be of the same order, and they are already given over here. They are already given over here in the figure itself. So these are the steps of 2 centimeter, 2 centimeter everywhere. Bas uska reverse, I mean T1 left side mein aayega. So T1 to T9 readings are over here. यहाँ पे इतनी सारी readings है. These readings will be over here. You need to take down some suitable scale, maybe 20. I mean कुछ तो एक suitable scale लेके यहाँ पे temperature ले लो and take down this step. Select thermocouple number 1. Select T or not T1. So thermocouple number 1. So let's take down. This is 2 centimeter, 4 centimeter, 6 centimeter, 8, 10, 12, 14, and carry on. 20 length in terms of centimeter. Length in terms of centimeter. And at this 2 centimeter distance, the temperature may be about, say, we have that reading. How much is that? It is 65.3. So the temperature will be at this much distance, 63.3, 65.3 something, 65.3. Then at 4 centimeter, it is 63.7 something. At 6 centimeter, it is, I mean, in that way, your plots you will get, and these will be the readings over here. And the nature of the curve will be something like this. This will be the nature of the curve. And at any distance, you know, this dt by dx is again the function of x, so value of dt by dx also changes with respect to the x distance. So wherever you want to take down the dt by dx, the value of dt by dx at that particular location. If you want to take down the dt by dx over here, take down the slope of the curve at this place. If you want to check out the dt by dx over here, check out the slope over here, and probably the slope may not be the same. And that's the reason dt by dx, the temperature gradient at every point along the length of the rod is not same. Why it is so? This is due to many reasons. This is due to the loss of heat in the radial direction and many parameters. We shouldn't go into that much detail. Right? At the end, you need to draw the graph, and in the conclusion, you need to write down these parts. The cooling water flow rate, it's over here. The heat lost from for our experiment, the cooling water flow rate, we got this flow rate to be W is 2.5 into 10 to the power minus 3. Let me write down what are the value we got for our experiment. 2.5 into 10 to the power minus 3. Then heat loss from the metal rod. So we got that heat flow rate as equal to 23.03. This is 23.03. And the thermal conductivity, we are getting it to be 569.69. Is that okay? Hello? Am I audible to you?
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Am I audible?
Yes, sir. You audible, sir.
Oh, मेरा वीडियो ऑन नहीं था क्या? Okay, anyway, video is not important. ठीक है, so I think you got the clear understanding of performance of this practical. If you have any doubt, any question related to this, you can ask me.
Sir, do we have to update these readings in our write-ups now?
Yes, you do one thing. You have also taken one reading from that video. You take down that reading for your calculation purpose and find out what is the value of K you are getting.
Yes, sir.
Right? One more thing. Okay, ये practical तो भी खत्म हुआ है, तो I will stop the recording of this video, and then we will have some informal discussions. Right? Just a minute.